Good afternoon, everyone. For the next 1 hour, get ready to delve into the modern world of multiphysics modeling focusing on semiconductor packaging. My name is Manpreet Kaur, and I will be moderating this exciting live webinar titled Multiphysics Simulation in Semiconductor Packaging. Here, I take this opportunity to introduce our esteemed speaker, Sharath B.N., Application Manager at COMSOL, who will be the speaker for this webinar on behalf of Dr. Sundar Namala. Due to some medical emergency, he couldn't orate this webinar. Hence, we welcome Sharath, who will be the prime speaker for this 1 hour innovative webinar. To give a brief introduction, Sharath P.N., an application manager at COMSOL's India office, received his master's degree in machine design from BMS College of Engineering in Bengaluru. Before joining COMSOL, he worked on mechanical integrity assessments in Siemens gas turbines at Tata Consultancy Services. During the webinar, requesting everyone to share their questions with their respective names and companies, you can directly write in the chat box. Also, we will be conducting 3 polls during this 1 hour webinar, so don't forget to share your opinions. We will be providing the information about the presentation on demand after the webinar. You can share your interest to us by writing at info@theworldpost.com. Subject presentation information of COMSOL webinar. And now allow me to welcome our esteemed speaker, Sharath, who will be starting the presentation and sharing live demonstration during this 1 hour webinar. Sharath, requesting you to share your screen and start the webinar.
Yeah, so thanks, Manpreet. I hope my screen is visible to everyone.
Yes, your screen is visible.
Okay, yeah, thanks for that kind introduction. And so, first of all, we'll start off by thanking WorldPost for giving COMSOL the platform to showcase its capabilities when it comes to semiconductor packaging. So, first of all, I would like to welcome all the attendees and would like to thank them for taking time, basically to see capabilities of COMSOL when it comes to semiconductor packaging. So we'll see how taking a multiphysics approach to modeling such phenomena could greatly benefit your organization, right? So it can greatly cut down on prototyping time or even the manufacturing times as well, right? So by to a great extent reducing the wastage and hence the cost that can be cut down when it comes to the business side as well, right? So we'll switch over to the presentation itself. I mean, in the interest of bandwidth, I'll be switching off my video camera. All right. When it comes to semiconductors, integrated circuits have become, kind of indispensable in modern life. So powering most of our devices, right? So everything ranging from smartphones and medical devices to very large systems such as automotive systems and also industrial equipment as well. And as the demand for a smaller, faster, and more reliable electronics grows, the role of semiconductor packaging has become increasingly critical. So not only for protecting the integrated circuits, but also for ensuring their thermal, mechanical, and also electrical performance. And advanced packaging technologies such as the recent what we refer to as the flip chips, the 3D ICs, and through silicon vias, which is commonly referred to as TSVs. Right? So these present new challenges in design and reliability. So the main agenda of this particular webinar is to leverage COMSOL multiphysics capability, right, to simulate and analyze key aspects of semiconductor packaging, including, let us say heat dissipation, stress distributions due to it could be warpage or residual stresses, and also interconnect integrity. Right? So with the goal of optimizing performance and ensuring long-term reliability in any real-world applications. So yeah. Moving on, so let us see a brief overview of some of COMSOL's capabilities when it comes to different aspects of semiconductor packaging. Right, so it could be in processing, it could be in performance, or it could also be to an extent in testing as well. Right, so when it comes to the processing part, what we refer to as the through silicon vias, right? So this is a vertical interconnect technology that allows electrical signals to pass through the silicon wafer rather than around it. Right, so this basically enables 3D chip stacking and high performance, high density packaging. So when it comes to the reliability part of it, right? So under the performance, so this basically refers to the ability of a packaged IC to perform its intended function over its expected lifetime, and preferably extended lifetimes as well, right? And under specified environmental and operating conditions. Yeah, so when you are referring to the preconditioning, right? So under testing, so it is a standardized process used in semiconductor manufacturing to simulate the environmental and mechanical stresses as well that your device may experience during board assembly and solder reflow, right? So this is typically done during the testing process itself, such as the HAST, TCT, or PCT processes or frameworks, right? So this is the broad overview of the semiconductor packaging simulations that can be done in COMSOL. So, I mean, before we move on to the main aspect of it, so just to gauge the kind of audience that we have for the webinar today, I would like to request Voltpost to launch this particular poll question. Right. So here the idea is to assess if you are new to any sort of multiphysics simulation, or if you are evaluating any simulation tools for your ongoing or upcoming project, or if you are just attending the session out of your personal interest, or you're a regular user of any other simulation tools. Probably we can take 20 to 30 seconds for this particular poll question. So Manpreet, can we continue now?
Yes, we can continue.
Okay, great. Yeah, so now that we have a good idea of the kind of attendees we have for this particular webinar, so let us now address the very fundamental question: what is multiphysics, or as an extension, why multiphysics? Right. So typically, if you take any example, right, if you consider an example of an electric motor itself, typically when you're starting off with the design of an electric motor, so you start off with the basic electromagnetic design, right? So once that is done, so we need to extend that particular design by considering the thermal management aspect of it as well, right? So because any electromagnetic device is prone to certain kinds of losses, right? It could be hysteresis or eddy current losses and so on, and we need to see what is going to be the temperature rise because of such losses, and it is essentially very important to consider the thermal management aspect of it. So once you bring up this particular topic, so then we need to think about what kind of cooling mechanisms we need to employ, right? So depending upon the magnitude of the losses, so it could be passive cooling or even active cooling as well. So then comes the CFD part, or what we refer to as the conjugate heat transfer part. Right. So once that is done, so next aspect of it is typically to see the different electromagnetic forces that are emanating from this motor operation, right? So that can basically lead to vibrations in the motor casing. So that can be further transmitted to the adjoining domains as well. So if it is an electric vehicle, for example, so here you are concerned more about the vibrations emanating from this motor to the adjoining chassis, right? So you want to minimize that as much as possible. So what I mean to say is, if you're starting off designing of any component, right, of your larger system, you need to not only take care of the fundamental physics, but also all the extended physics as well. So that is where the multiphysics aspect of the simulation comes in, right? So in this particular webinar, we'll see how multiphysics is going to help when it comes to the semiconductor packaging aspect. So within COMSOL Multiphysics, so you don't have the option to, what I mean to say is you have the option to not only model the multiphysics of your system, but also the single physics aspects of it, right? So COMSOL gives you the flexibility to model the governing equations of individual physics, and also to couple the governing equations between the different physics. For example, if you're modeling electric currents and heat transfer, which is a multiphysics system. So then you are modeling basically the heat sources because of, let us say, ohmic losses to the heat transfer to basically compute the temperature rise, right? That kind of unique functionality is what COMSOL Multiphysics provides in a single platform, right? So you don't have to switch between multiple softwares to perform such a multiphysics analysis. All right, so now moving on to the actual topic of electronics packaging itself. So in this slide, you are basically seeing the major multiphysics phenomena that are critical in advanced semiconductor packaging, right? So basically, as integration densities within your integrated circuits increase, packaging must account for basically thermal, mechanical, electrical, and also in certain aspects chemical interactions as well, right? So COMSOL provides tools to simulate these coupled effects, thereby improving performance, reliability, and also manufacturability. Right? So when it comes to the TSV manufacturing itself, what we refer to as through silicon vias, right? So we model the key steps such as the photolithography process. It could be etching, film deposition, or even the planarization part. So all of these can be modeled, right? So these processes typically involve thermal and mechanical stresses that can lead to defects, such as the deformation of copper protrusions, right? So these needs to be optimized. And basically hybrid bonding that you see here. Yeah, so the hybrid bonding that you see here, yeah, so basically so these hybrid bonding processes basically help you to optimize the different properties, such as it could be surface preparation, adhesion properties, and even the air gap effects as well, right? So flip chip bonding is one of the modern day electronic bonding methodologies that is available, basically due to its lower what we refer to as electrical impedance, right? So flip chip packaging simulations can also be done, so which basically as a manufacturing process introduces residual stresses and warpage, right? So especially due to thermal mismatch and some aspects of underfill curing as well, right? So in COMSOL you can basically accommodate all these underlying interactions and model your system in a very accurate way, right? So yeah, yeah, and also certain aspects of reliability as well, right? So COMSOL models different failure mechanisms such as copper protrusion, or it can be basically cracking in these TSVs, right? So it can also be thermal fatigue in your weld bumps, or even the electromigration due to high current densities, right? So these phenomena can be basically you can include these phenomena. And by combining all of these phenomena, you can basically help predict the lifetime and ensure robust design for your ICs, right? Yeah. So when it comes to passive and active cooling methods for your thermal management, so that is also possible by integrating different CFD and heat transfer phenomena, right? And also when it comes to the electrical performance, signal integrity is a very important key factor, right? Especially at high frequencies. So we can model equivalent RLC parameters, or it could be impedance mismatches, and also crosstalk between signal lines, right? So these simulations are very crucial if you want to model a robust system. So now that you have broadly seen the different aspects that can be, basically modeled in COMSOL, so we would like to know, so what exact phenomena you are interested in modeling in COMSOL, right? So that we can better modify the further content. So I request Manpreet to launch the second poll question here. Basically, just to know if you are more interested in modeling the etching or the reflow soldering, warpage and residual stresses, if you're more interested in reliability and preconditioning, or if you have any other topics, so please specify it in the relevant section so that we can take up the discussions even after the webinar as well. Yeah. So thank you for answering the poll question. So moving on. So now, when it comes to the semiconductor processing, so etching is one of the very, primary steps, right? So in that case, if you refer to the wet etching itself, which you see on the left, these are typically anisotropic in nature, right? So, and the graphic that you see here is from one of the COMSOL models itself. So it basically simulates the wet etching of silicon in potassium hydroxide solution. So in this slide, so we are basically exploring the fundamental process in the semiconductor packaging used to create different features such as vias, trenches, or cavities, right? So in materials such as silicons, oxides, or even polymers. Yeah, so once again, so this is what you see here is a time lapse, right? So starting from t is equal to 0, t point 4.8, t is equal to 2 minutes, right? So you see a time dependent process that is happening basically because due to the wet etching here, right? So here basically this involves immersing of the wafer in a chemical solution, right? So this purely relies on chemical reactions and mass transport to remove the material. So when it comes to the wet etching simulations, the key modeling aspects here include the etching depth over time, as you can see in the graphic. It also basically isotropic, right? So meaning the etching occurs equally in all the directions, and the impact of reaction kinetics and diffusion in the liquid phase, right? So all of these can be modeled in the software, right? Yeah, so though this method is quite simple and cost effective, the downsides being it is harder to control the precision and also the geometry of the etched features, right? But on the right side, what you see is an improved process, right? So which is basically the dry etching, which involves plasma, right? So we use plasma to remove the material under a vacuum environment. So this in COMSOL is modeled by simulating the plasma chemical reactions, particle trajectories, and also the surface interactions as well, right? So here the key parameters that you will be looking for after the simulation is the selectivity between different materials. So basically, you can control the direction in which you want to basically model your etching, right? So which is anisotropic. Yeah, and also the ion bombardment effects, right? So the plasma ions, which require tracking of charged particles in the plasma, right? So this is a much more controlled and is very essential for high aspect ratio features, right? So basically for advanced packaging processes such as the TSVs and also RDLs, or what we refer to as the redistribution layers. Right? Yeah. So this is one of the important phenomena that can be modeled in COMSOL. Yeah, so in addition to etching, so we can model different kinds of soldering processes, right? So this slide essentially highlights that how we can simulate them using COMSOL, right? So typically this is used for die attachment or any interconnect formations, and also component level bonding as well, right? So all of which influence the thermal, mechanical, and also the electrical reliability of your end component as well. So on the left, what you see here is a simulation of the molten pool behavior, which occurs during the traditional solder reflow, right? So here, the important parameters could be the melting rate, evaporation, sublimation, and also ultimate solidification as well of the solder material. Right. So here you can model the multi-phase flow with phase changes, right? So which essentially governs how the solder wets the substrate. You can also, basically track the pool depth and width, right? So which is critical for the joint integrity, and also certain defects such as keyholes and gas inclusions, right? So which can be predicted based on the process conditions as well. So understanding the molten pool dynamics basically helps you optimize the temperature profiles and also avoid incomplete wetting or voids within these solders. Right. So when it comes to the laser heating, the spot size and energy density is one of the critical process parameters, right? And also the pulse duration as well, which influence the thermal gradients. Right. So if you're talking about the focus shifting, so this process parameter basically affects the uniformity and penetration of the heating as well, right? And ultimately, if you look at the ultrasonic welding, this basically uses mechanical vibrations to create frictional dissipation and heat at the interface of your basically PCB and the wire bonds, right? So here you can take into account the frictional heating and also the plastic dissipation as well. Right. So ultimately here you need to model the thermal contact very accurately to capture the results. Right. So yeah, I mean, ultrasonic welding is particularly suitable for applications which involve flexible electronics, right, or thermally fragile components, where you cannot basically take it to very high temperatures using the conventional soldering methods, right. So using COMSOL, essentially you can simulate these interactions in very high detail, right. So and ultimately helping the researchers or engineers to fine tune their process parameters so that you can get higher reliability, uh, basically because of stronger joints and also better energy efficiency as well. Yeah, so in between, if you have any queries, so please feel free to type in the question section. Probably we can take those questions up at the end of the webinar. All right, so here we are basically looking at the mechanical or structural and material level changes that we need to model, right, and that essentially occur during the soldering process, right, in the packaging process. So here, as you can see in the slide, COMSOL enables the simulation of how different heat, thermal properties, material properties, and structural behavior interact during the soldering and also the post-solder curing as well. Right. So first, if you look at the thermal stress and deformation, basically the solder joints and the surrounding materials experience thermal expansion, right? So leading to strain, warpage. So especially warpage is a critical, parameter that we need to take care of during the manufacturing, right? So in COMSOL, we can simulate the multiphysics behavior, right? So which involves thermal stress and strain due to temperature gradients. So it can be residual stresses after solidification, and the residual stresses is also a combination of different phases as well, right? So different solid phases itself. So between phase transformations that can lead to, basically transformation induced strain, essentially leading to residual stresses as well. Yeah, so for that we have a dedicated metal phase transformation module, right? So where you can model the different solid phase transformations itself. Yeah, so coming to the structural damage that you see on the right side, you can model different forms of interfacial delamination between, let us say, the solder and the substrates as well, right? So there can be crack initiation and growth because of residual stresses, especially under cyclic thermal or mechanical loads. So you can also simulate different macroscopic defects such as voids, which can ultimately degrade electrical and mechanical performance as well. Right? So we need to consider all of these aspects in mind if you want to improve the package robustness and essentially extend the product lifetime. So in continuation of the previous slide, so we have one example model within COMSOL library. Right. So to all the attendees, if this is your area of research, I urge you after the webinar to essentially explore this particular model to see how the different governing equations are considered while solving this particular model. Right. Yeah. So here we are basically simulating the residual stress and warpage in a printed circuit board after the reflow soldering process, right? So during the process itself, the solder balls are first melted and then solidified to form both mechanical and electrical connection between the package and the PCB, right? So, but during the cooling process, the residual stresses develop due to mismatches in the thermal expansion coefficients of different materials. Right, so this essentially leads to warpages and can cause to alignment issues, mechanical strain, and even connection failures as well. Right, so you can model such phenomena in COMSOL. Right, so COMSOL also has the activation feature, right? So which I can say is unique to this particular software. Right, so using this feature, so you can basically simulate time-dependent inclusion or exclusion of material properties, physics, features, or even the geometry itself. Right. So, basically, this feature allows for a time-dependent material property changes as well, which ultimately enables you to have a precise simulation of phase change behavior and also its ultimate mechanical consequences as well. Right. So yeah. So this is a very good model for you to explore after after the webinar itself. All right. So in continuation of the previous slide itself, so COMSOL also has a general purpose optimization feature, right? So it could be optimization of different parameters, it could be shape optimization, or even the topology optimization as well, right? So where by keeping in mind a certain objective function and a set of constraints, you're basically trying to achieve a set of objectives here, right? So here here basically the ball grid array technology is used, right? So for the surface mounted technology, so here there are two types of solder balls that you see here of different colors, right? So one is for the functional, essentially to produce a electrical continuity, and other is for basically the mechanical strength, right? So essentially the support balls that are used only for reinforcement, right? So here optimization study is done to basically optimize for the placement of the support solder balls, right? So that the warpage is minimized. So here the objective function is to minimize the warpage, while we are trying to basically optimize for the placement of the solder balls, right? Yeah. So this once again basically makes use of heat transfer, structural mechanics, and also the optimization physics interfaces. Yeah, so in continuation of the packaging process optimization, so this slide basically covers the simulation of underfill process, right? So in advanced packaging. So underfill materials are critical in the flip chip and 3D packaging to basically improve the mechanical support, thermal performance, reliability by basically filling the gap between the die and the substrate, right? So that is what you see here. So they typically exhibit non-Newtonian behavior, right? So in COMSOL we have different material models and also thixotropic models for fluids, right? So it could be viscoelasticity, shear thinning or thickening, and also like I said, different solid material models as well, right? So here the flow could be essentially driven by either external pressure or even capillary forces as well, right? So the fluid flow here, and the effect of temperature on fluid properties, which influences how easily the underfill spreads, right? So all of this can be modeled, and you can also through simulation basically predict the void formation as well. So basically this is because of incomplete filling or irregular flow, especially in narrow gap regions, so between the two layers, right? Yeah. So this also once again is a highly multiphysical phenomena, right? In the sense it also involves chemical curing process, right? So basically whatever the underfill you're flowing between the two layers, so that is ultimately cured by a chemical curing process, right? So basically, you need to solve for reaction kinetics, typically Arrhenius type equations, right? So all of this is can be very easily done within COMSOL because you're essentially doing it in one single graphical user interface, right? Yeah, so basically during and after curing, so what is the kind of mechanical deformation that can be expected, right? So and volume shrinkage and also the various thermal effects as well, right? So all of these can be basically analyzed. Yeah, so this is an example model that we have in COMSOL, right? So this is basically evaluating for the residual stresses and also warpage due to the curing of the underfill, right? So once you inject the underfill and after the curing process, what are the different kinds of deforming loads that it is basically applying on your PCB, right? Yeah, so this can be modeled, and basically during the curing process, the volumetric shrinkage that occurs as the fluid transitions from liquid to solid, right? So you can also model the material properties such as the elastic modulus or thermal expansion coefficient. That is also essentially a function of temperature as well, right? So that can also be modeled here. All right, so we'll go to yeah, probably the next section here. So this basically simulates, basically the mechanical aspects of it, right? So that being specifically for grinding, dicing, and molding, right? So that being the finishing processes of the semiconductor processing itself, right? So first, if you look at the grinding and dicing processes, so which are essentially for thinning wafers and basically singulating dies, right? So In COMSOL, you can model toolware because of such grinding process, right? Or it could also be the wear in the wire source as well, right? So which essentially impacts the surface quality and also the die yield. So you can also model the laser dicing as well, where you can model the heat affected zones and also the thermal induced stresses as well. We already covered on the warpage and the cracking and also the edge chipping effects as well. So which are critical failure modes during the die separation itself. So we'll see that in the subsequent slide. So it is also influenced by the cooling method and the cooling rates as well, right? So on the right side, what you see here is the molding process, right? So where the encapsulant, which is typically for a PCB, it is usually epoxy, right? So it is injected into or around the die and wires for protection, right? So by using the multi-phase flow of the CFD module, you can model the compound filling of the cavity during the curing process, right? So which once again includes chemical cross-linking and also heat generation during the curing itself. Right. So you can also model the demolding mechanics as well, which includes the stress buildup and release, which can lead to a package warpage or even the delamination as well. Right. All right. This is another example that we have. Which is basically on the evolution of warpage modes, right, during epoxy molding process. So it is a critical issue in manufacturing of electronic packaging, right? So being the warpage, so which may cause defects such as poor solder joint contact, or it can also lead to die cracking or even circuit breakage as well. Right. So thermal mechanical performance of such EMC, or what we refer to as the epoxy molding compound, during the molding process is the main factor that affects this, right? So in COMSOL, so this kind of simulation is modeled using the generalized Maxwell model, right? So this basically models or represents the viscoelastic stress relaxation behavior of the epoxy molding compound. Right. So this essentially allows us to capture the time-dependent deformation and also the delayed elastic effects, right? So which is especially important during cooling and post-cure, right? So you can also see the different warpage behavior at different temperatures, right? So you can see the effects of it as well in a graphical representation. Basically, temperature changes during the molding. Yeah, so once the molding is done, the next step would be the demolding, right? So in this model, it is essentially done using the ejector pins, right? So this model that you see basically demonstrates the process of ejector pin demolding itself, right? So where the initial product and the mold are so basically in contact with each other and othered together by the cohesive force, right? And basically the mold is then detach from the product itself by pushing it using the ejector pin, right? But during demolding itself, the mechanical interaction occurs at the interface between the EMC and the mold tool, right? So I mean, this can also cause potential interfacial damage as well, right? So if you are not placing these ejector pins in the right locations. So you can consider the different cohesive zone models, or it can be the different traction separation laws, which govern how the interface between EMC and the mold responds to during application of such loads, right? So basically this is simulation to improve the performance during the manufacturing itself, right? All right, so here you can also see the variation of the force applied on the ejector pins during the demolding, right? Yeah, so we need to model the contacts as well accurately. All right, moisture and humidity, so they play a vital role, right, in packaging reliability. So particularly in environments where such devices are exposed to varying thermal and also humidity conditions over time. Right. So here the major contributors to packaging stresses are essentially the thermal expansion, right, and also due to the vapor buildup from evaporation, right. So typically during such injection molding process, there could be some amount of trapped moisture inside the package, right, and during operation, so this moisture can evaporate under heat, essentially increasing the pressure inside and leading to delamination or cracking as well, right? And also the hygroscopic swelling, right? So essentially these three phenomena is what controls the reliability of your package, right? So certain materials typically absorb moisture, causing them to swell, and this can cause certain stresses on the adjacent components, right? So in COMSOL you can basically model such a highly multiphysics phenomena by considering the different effects of heat transfer, moisture transport. It could be hygroscopic swelling and also the thermal expansion, right? Yeah, so we have dedicated models which covers all of these multiphysics aspects. So which I urge the participants, basically to explore after the end of the webinar. Yeah, so when it comes to accurately modeling the structural response, right? So it is very crucial to consider the accurate material model, right? So that is because after a certain point of loading, the material basically exhibits a certain nonlinear behaviors, right? So for that, when it comes to metals, it could be basically deploying the plasticity, or for materials such as the solder alloys at high temperature, it could be the creep and viscoplastic behavior, right? And during the underfilling of the interfacial layer, the material models of viscoelasticity becomes very crucial, right? So all of these can be captured by using the different nonlinear structural material models that are present within COMSOL Multiphysics. Yeah, in continuation of the structural simulations as well. So basically, you can model different modes of failure as well. Which basically affect the long-term reliability and performance of these devices, right? So it could be the interfacial delamination, right? So which basically means the separation at the material interfaces. So since you'll be using a very thin layers, so these are prone to separation at the interfaces, right? So this could be due to any of the reasons that we discussed in the earlier slides, right? So which is very common in the epoxy molded molding compounds as well, right? So it is also, there is a certain risk of cracking as well, right? So basically COMSOL has different approaches within fracture mechanics to estimate the probability of crack initiation under different stress and strain concentrations, right? So basically that is done using either J integral approach or stress intensity factor, or even the energy release rate approaches, right? Yeah, so you can also assess the risk of cracks as well, right? So once the crack initiation is done, so then what is the risk of failure due to the crack propagation itself, right? So that is basically done by using the approaches such as the phase field damage method, right? So this is very essential for assessing the long-term mechanical fatigue and also the crack-driven failures. So you can also assess the different thermal fatigue effects as well, right? Especially at the solder joints, which is what you see here. Yeah, I mean, for the surface-mounted devices, so before the actual reliability testing, so these devices are required to go through a certain preconditioning process, right? So this could be, so this basically represents the effects of storage and the typical reflow operation in the following board assembly processes. Right? So during the preconditioning process, the test samples are subjected to thermal cycling, or dry baking, moisture soaking, and also the solder flow operations as well, right? So the model or the animation that you see here, basically represents that particular model, right? So here you can see the stresses caused because of moisture diffusion and also the warpage. So because of the different forces that are acting on it, right? Yeah, so you can also see the distribution of vapor pressure. So when there is when the temperature increases, and basically the pressure, the vapor pressure inside your epoxy mold increases, right? So you can also see the distribution of vapor pressure during such a phenomena. Yeah, so coming to the extended simulations for reliability. So one such simulation that you can do before the actual physical simulation is a shock and vibration testing. Right, so you can perform different kinds of frequency domain studies for base excitation to analyze the system responses. Right, so you can also model the dynamic, responses because of impact events, or even to assess the shock responses. Right, so we can also perform random vibration analysis as well. Right, so to simulate real-world vibration conditions and to assess the impact on package reliability as well. Right, so we have many standard models that are available within the application libraries. Right, so this is one such example of shock response of a motherboard itself. Yeah. So not just for the dynamic loads, you can also assess your electronic components for static loads as well. Right. So yeah, basically the loads can be bending loads, torsion loads, or even in the form of pressure loads as well. Right. So this is a graphic that you see here is for a 4-point bending test. Right. So that is a very common and a conventional test method used to test the mechanical properties of materials subjected to such bending loads. Right. So, and it is also a typical reliability test that are used for such semiconductor devices as well. Right. So for packaging and assembly. Yeah. So this is essentially for of an IGBT module where we are conducting such 4-point bending test. Yeah. All right. So so basically, when it comes to large models, they cannot so often cannot be meshed to a very fine extent, right? So because there is a computational cost to it as well as the refinement goes high. But when it comes to the electronic devices itself, there are many critical areas, right? So that we need to mesh in a very fine manner so that we are able to resolve the solutions to a very higher accuracy. Right. So here we need to basically take a 2-step strategy. Right. So first is to solve for a global model with a coarser mesh and get an overall solution. So this is the global model. Right. But once we see that there are certain stress concentrations in these solder balls, for example, so then we need to create a high resolution submodel. Right. So that is what you see here. So this submodel will basically have a very high refinement of mesh. Right. So this we do to basically do a very detailed analysis. These submodels basically use the global model solution as boundary conditions. Right. So basically in COMSOL, this particular method also supports multiphysics simulations. Right. So it could be nonlinear material behavior. You can also include the static and dynamic analysis. Right. Yeah. So all of these can be done. I mean, this slide is to basically highlight on how we can basically solve for a coarse mesh at the global level, but do a submodel analysis and get very accurate results at the very local level. Right. All right. So that was on the heat transfer, on the structural aspects of it. Now coming to some of the heat transfer capabilities in COMSOL. So I mean, typical heat dissipation mechanisms are conduction, convection, and radiation. Right. So when it comes to conduction, so COMSOL essentially supports isotropic, anisotropic, linear, nonlinear thermal conductivity. Right. So you can also model the thermal contact resistance as well. Right, so which is typically applicable for thin structures. So you can model different convective effects as well. So it could be free or forced convection, right? You could also include the turbulent flow regimes as well, right? So when it comes to the conjugate heat transfer part, and also you can consider different aspects of radiation, being the surface to ambient radiation, surface to surface, and also so the radiation in participating media is also supported, right? So where the medium itself absorbs or emits radiation, right? All right. So coming to the multi-physics of such heat transfer, simulations. So you can capture the multi-physics effects of ohmic and eddy current losses, right? So typically this happens in the functional components such as bonding wires or even the solder balls itself, right? So we can also consider various hysteresis and dielectric losses due to magnetic domain realignment, right? So these are especially significant for RF devices where alternating fields cause energy dissipation. So you can also consider the temperature sensitivity as well, right? You consider copper material, right? So where the conductivity varies drastically with temperature, which influences once again heating and the magnetization behavior of the material as well. right? So all of these can be considered. All right. So when it comes to the thermal management of your electronic devices, so you can model your heat dissipation either using the passive or active methods, right? So passive being the modeling of the fins itself, the cooling fins. There are certain features available within COMSOL to model thermally thin shells. So you can also model fans and grills as well, right? So that is what you see here. You don't have to explicitly model the fans along with all the fan blades and so on. So there are certain features, simplification features available within COMSOL, where, for example, if you know the fan pressure curves or loss coefficients, you can basically give that as an input to your boundary condition and perform the simulation. So this is one such analysis. So we can also model non-isothermal flow within your micro fluidic devices, and also model a non-isothermal flow in porous and free media as well, right? So which is typically what we see in heat pipe applications. Yeah, you can also model your devices in a lumped system as well, right? So also for thermal, basically to simplify your complex models by essentially representing the thermal behavior with lumped elements. So it could be in the form of thermal resistors, capacitors, or heat sources, right? So essentially, it reduces the computational complexity while at the same time capturing the key thermal dynamics, right? All right, so this is another example model that we have on how you can use the lump thermal setup consisting of a thermoelectric element and computes the non-isothermal flow around its heat sink, right? So yeah, so in COMSOL we also have what we refer to as add-ins, right? So basically, PID controller is an add-in that can be used to stabilize the temperature to a predefined value, right? Yeah, you can also see the junction temperature stabilized by the TEC system itself. All right, so like I was mentioning is one of the earlier slides. So optimization is one of the key features that we have, right? So yeah, so we have different range of examples that covers different physics as well, which I urge you to explore after the webinar. So when it comes to the electromagnetics, so equivalent circuit modeling is one of the key features that are available, right? So it models the interconnect structures using the equivalent RLC matrices at different frequencies, right? So you can also account for skin effects as well, skin effects and proximity effects, right? So where the influence of nearby conductors on different electrical parameters. So if you're more interested in performing signal transmission characteristics, right? So to analyze reflections, crosstalk, losses, or even the distortions occurring during the signal transmission within the interconnects, right? So those kinds of simulations can be performed. Yeah, so when it comes to the electromagnetic modeling, so we have the electric circuit modeling as well, right? So which enables coupling of lumped circuit systems to the finite element models as well. It also supports the import and export of SPICE netlists, right? So for circuit simulation interoperability, and you can also import different forms of ECAD file formats as well for your PCBs. So these being IPC and ODB plus file formats, so which are very popular. Yeah, you can also perform emission and immunity analysis for your PCBs as well, right? So when you're giving some sort of excitation in one of the the copper trace and see what is going to be its effect on the adjacent copper traces, right? So such immunity response can also be done. Yeah, so right. So moving on, so electrostatic discharge simulations, right, of a PCB is very essential, and it is typically very expensive when you go for an actual physical testing, right? So I mean, ultimately, if you have to go for a physical testing, you can basically cut down on such testing times and also the iterations by performing the simulation beforehand, right? So this example basically performs how an electrostatic discharge event causes a logic error of a microchip on a PCB board, right? So here the electrostatic discharge current is based on an extended human body model, right? And it is predefined in the lump port feature within COMSOL. All right, so this is basically different modules that are present in COMSOL Multiphysics to carry out different sorts of either single physics or multiphysics analysis, right? So yeah. Now, let us quickly go on to a quick demonstration model. All right, so what you see on the screen here is a model of a heating circuit, right? So this typically consists of certain base layer here, which is made out of silica glass. So then we have a very thin layer of silver for the interconnects and also a nichrome layer. So that is what you see here, right, of this particular shape. So this is the basic GUI of COMSOL Multiphysics itself, right? So on the left, what you see here is a model builder itself, and as the name itself suggests, so it has the different steps that essentially you need to take to set up your simulation model, right? So basically, it involves basically creating your geometry within COMSOL or importing it from any other external sources using this particular geometry node here. So then comes assigning different materials for the different domains, right? So COMSOL has a very large material library consisting of up to close to 14,000 different material properties. So then comes the boundary conditions, right? So that is essentially done by using different physics interfaces within COMSOL, right? So in COMSOL, the boundary conditions are basically segregated based upon the physics interfaces, right? So here a heating circuit model is essentially a multiphysics phenomena that involves the solid mechanics or the structural component of it. It also involves the heat transfer, and it also involves the electric currents, right? Electric currents, basically, there is a excitation potential on one end, and the electric current flows through this particular strip, and because of its inherent material property, it causes temperature rise because of ohmic losses, right? And we are typically trying to simulate the temperature rise because of the electric current and also the thermal dissipation into the adjacent solid domain, and we'll see how all of these phenomena are typically coupled, right? So within COMSOL. All right. So, in the interest of time, I'll be a little, fast-paced in setting up this particular demo model, right? So, first of all, we'll start off with, material properties itself, right? So now, coming to the materials itself, this particular base layer that you see here is formed by the silica glass material. So I'll go to silica glass and assign this particular domain. So coming to the silver layer, so I'll be assigning these two domains here. So this is basically a boundary material, right? So which essentially represents a very thin material. And this particular strip is made out of nichrome layer. And you can also see the different material properties being used, right? So if you go to the silica glass itself, COMSOL is basically using the heat capacity, the density, thermal conductivity. So these three being the thermal properties, the Young's modulus and Poisson's ratio, and also the density for solving the different structural mechanics equations, right? So similarly for the silver layer, the only addition being the thickness, right? So since it is a very thin or the high aspect ratio component, so we need to define the layer as well, right? So for both nichrome and silver layer, we have essentially defined different thicknesses. So coming to the solid mechanics itself, so we need to assign certain boundary conditions, right? So one thing is under solid mechanics itself. So we are essentially modeling it using 3D elements, right? So for the solid domain here, we are modeling using 3D elements. But for these thin strips of these traces, right? So we need to model it using the thin layer feature within COMSOL. Right. So once I right click on solid mechanics, you can see the different material models, volume forces, and also the different boundary conditions as well. Right. So for now, I'll go with the thin layer, and I'll assign. All right. So just give it a second. So since this is a conference machine, probably it is taking up some resource. All right. So within the thin layer, I'll be assigning these boundaries, right? So where my thin copper traces are, right? So once that is done, I need to constrain the motion of this particular device, right? So for that, so we have different constraints, right? So it could be prescribed displacement or a fixed constraint and so on. So for now, I'll be going with a domain constraint, basically to suppress any rigid motion. Right. So then we are basically also interested in knowing the warpage effects as well because of the heating here. So I'll also add another warpage boundary condition here. Right. So this is essentially for the bottom layer. Right. So I want to see what is going to be the warpage due to the heating of the top trace. Right. So I'm assigning this particular boundary to warpage. Right. So now moving on to the heat transfer in solids. So here, once again, I need to assign a thin layer here. Right. So I'll right click on it, and I'll probably go to the thin structures and to the thin layer here. Right. So once again, I need to select the thin copper traces here. Right. So then I need to model some sort of heat dissipation mechanism as well. Right. So you can either explicitly model in a conjugate heat transfer model, or here you can essentially model it using a heat flux boundary condition. Right. So we can have different boundary conditions for the top and bottom, assuming that if you are modeling some sort of fluid flow at the bottom layer, so then you need to give the corresponding heat fluxes, right? So if I assign this to the top layer here, right? So yeah, so I need to model the convective heat flux, right? So and I need to assign certain heat transfer coefficients. So maybe for now, I'll assign 5 as the value here, right? Yeah, similarly, you can assign this particular boundary condition for the bottom layer as well, right? So yeah, and coming to the heat transfer, to the electric currents in layer shells. So here, the most important boundary conditions are the current excitation and the ground nodes, right? To complete the circuit. So first, I'll right click on this and give some sort of electric potential on one end, right? So probably I'll assign some electric potential here. So here, the value can be around, so let us say around 12 volts, right? And I need to assign a ground condition on the end of this particular trace, right? So here the equation is going to be 0. The voltage is going to be taken as 0. Right. So now I have assigned all the boundary conditions for the electric currents, heat transfer, and also solid mechanics. Now I need to basically couple these three physics interfaces, right? So for that we have different multiphysics couplings available. So first I'll be adding, thermal expansion. So once I right click on multiphysics, so based on the different physics interfaces that are involved, COMSOL automatically suggests the relevant boundary, the multiphysics couplings, right? So I'll add the thermal expansion first, and also add, basically the domain where I want to solve this particular equation, and also specify the heat transfer interface and also the structural mechanics interface, right? So these two interfaces are going to be basically connected by this particular coupling. Now the solid coupling is done. Now I'm interested in performing the thermal expansion in thin layers as well. So the thin layer being the copper trace here, right? Now here I'll be coupling once again the heat transfer in solids and also the solid mechanics, right? So, but here I'm more interested in modeling the layered shells here, right? So here once again I just need to change this particular thing to layered, right? So that is what we are modeling here. And now I'll be able to solve the thermal expansion within this thin copper trace here, right? So another multiphysics coupling that I need to consider is the electromagnetic heating layered shell, right? Because basically the current is being carried by this trace here, right? And I need to know what is the losses, electromagnetic losses because of the resistive heating, right? So I need to be coupling the electric currents in layered shells and also the heat transfer in solids, right? So now that I have set up the entire model, I need to mesh my particular component devices, right? In COMSOL, we have what we refer to as either physics controlled mesh or a user controlled mesh, right? So physics controlled mesh essentially based upon the different physics interfaces or the different equations that we are solving for, and also the different boundary conditions, COMSOL will automatically generate a mesh. Right. So if you are solving for example, let us say a fluid interface, COMSOL will automatically generate the basically the different boundary layers, right? So depending upon the wall conditions, so it could be if you want to know let us say the skin depth, right? So depending upon the boundary condition, COMSOL will once again create the mesh layers. So here it can range from extremely fine to extremely coarse, right? So what I modeled is normal. So you can also go with finer mesh elements as well, right? So that is on the mesh aspect. Of course, you can go with the user control mesh and get a better control over your mesh, right? So then comes the study type. So now if you go to the study tab, right? So essentially you can see all the different kinds of study types that COMSOL interface supports. So ranging from very basic stationary or time dependent to different frequency domain studies, and also different what we refer to as FFT solvers and so on. Right, so it could be frequency to time FFT, time to frequency FFT, and so on. It could be different eigen frequency solvers, frequency domain solvers, and so on. So for now, I'll be adding a stationary solver here, and I'll be solving for all of the physics interfaces, right? So ranging from solid mechanics, heat transfer, electric currents, and also different multiphysics couplings as well. Right. So keeping the limited time in mind, so we already have a solid model here. Maybe I'll just open that particular model. Yeah. So here, what you're seeing is essentially the solid model, right? Yeah. So what you're seeing here is the stresses developed due to the warpage, right? So here you can see the von Mises stresses. It is going up to 12 megapascals, right? So in these regions where you can see the highest, where you can expect the highest dissipation electromagnetically, right? So that is, it is the shortest path that the electric current is going to take, and that is where we are going to see the highest temperature gradients leading to higher stresses, right? So you can also see the stresses in the thin layers as well, right? So within the thin layers, it is going up to 350 or up to 400 megapascals here, right? And you can also plot for temperatures. So here the temperatures are essentially going up to 430 Kelvin here, right? So essentially the ohmic losses. You can also see the electric potential. If you remember, we applied 12 volts of potential, right? So that is what you see here, and there is a potential drop ultimately going to 0 volts at the ground. Right. And you can also plot the surface losses, the losses being the electromagnetic losses in watt per meter square units. Right. So the losses are going up to 12 kilowatt per meter square density. Right. The losses being highest where the current density is expected to be highest. Right. Yeah. You can also see the interface losses at the interface of the trace, and also basically the substrate itself. And ultimately, you can also see the warpage in your PCB as well, right? So basically here you can see that the warpage is maximum in these corners, right? So the warpage going up to 30 microns at the corners. So I mean, this was a quick demonstration. I mean, I apologize if it was very quick because of the time constraints. Maybe if you have any additional questions on this particular model setup, we can connect later as well. Through an online or a one-on-one interaction, right? Yeah, so this is once again a highly multiphysics setup that we have that consists of structural mechanics, heat transfer, and also the electric currents as well, right? So all of this done in one single user environment, right? So you're not switching between different softwares for performing different kinds of analysis. All right, so this is we have come to the end of the software demonstration itself. I'll be going back to my particular slide. Yeah, so essentially what we saw is that within COMSOL, when it comes to developing different semiconductor packaging solutions, right? So COMSOL can essentially, to a great extent, help you while performing, complex multiphysics simulations, right? So these simulations can be a combination that involves, basic electromagnetics to heat transfer to structural mechanics that can include vibrations, deformations, and also fluid dynamics if you are more interested in thermal management, right? So ranging from passive cooling to very active cooling that can involve complex non-isothermal flow, or what we refer to as the conjugate heat transfer analysis, right? So all of this can be done by considering the realistic operating conditions, right? So Yeah, so before we take up any further questions, I would request Manpreet to launch this final poll question. So just to try to understand your interest in trying to connect with COMSOL after this session, right? So if you're working on any current project and if you want to try to connect with us to find solutions for your complex problems, please reach out to COMSOL at support@comsol.com, right? Or you can directly reach out to any COMSOL representative, right? All right, maybe parallelly we can take some questions as well. So we already have one question. So how do you decide which physical phenomena to couple together in a simulation? Yeah, I mean, so like we saw in the demonstration model itself, right? So it essentially depends on what kind of phenomena that is occurring, right? So if you take an example of let us say a Joule heating effect itself, so you'll have to consider the physics of electric currents or electromagnetics. You'll have to consider basically try to estimate because of the electromagnetic losses. So that can lead to depending upon the cross section of your conducting wire, to what extent the losses can lead to temperature rise, right? So if that is going to be significant, so then you'll have to model certain thermal aspects of it as well, right? So just to see how that particular heat can be dissipated to the ambient, right? So yeah, so once that is your area of interest, the heat dissipation, so then you'll be looking at the CFD part, right, to see what kind of flow mechanisms or passive heat dissipation mechanisms to be included in your model, so that you can achieve the achieve the set target of temperature, right? At the same time, if you are interested in more in the let us say the deformations or the warpage aspect of it, then you'll be more solving or looking towards the structural mechanics aspect of it, right? So once again, it highly depends on what kind of uh, objective you have in mind to decide on what kind of physical equations that you're trying to solve or couple together. All right, so there is another question on can you talk about how meshing strategies differ for small scale packaging components, especially for 3D ICs or advanced packages? Yeah, so here once again, if you go back to one of the slides, right? So where we demonstrated on the concept of submodel approach. So essentially, if you are talking about scale, if you're interested in a region that is very small when compared to your larger system, right? So essentially you can go for very quick simulation of your larger system itself using a very coarse mesh. And then when it comes to the small scale aspect of it, right, it could be at the solder joints or it could be at the interconnects or at the wire bonding interconnects, right? So then you'll be basically looking at the submodel approach, so where you can go for very refined meshing strategy, right, or with a very large number of elements as well. It is not going to hinder your simulation time, right? So it basically depends on at what scale you are looking at your model. I hope that answered your question. If there are any follow-up questions, so please feel free to ask. So there is another question. So what's the best way to model heat sinks or thermal vias in advanced packaging designs? Yeah, I mean, so there are multiple approaches here, and like we saw in one of the earlier slides, so COMSOL offers very simplified, features to model, even advanced cooling strategies, right? Anyway, modeling heat sinks in the form of fins is fairly straightforward. But let us say you want to model any kind of very active cooling mechanisms, right? So instead of explicitly modeling for your different components within your active active modeling such as the different fans that can involve different sorts of fan designs or even blade designs. COMSOL basically provides features to model it as a single boundary condition on your boundary, right? So if you have let us say the pressure data from your fan supplier or manufacturer, then you can essentially use that data to perform your simulations, right? So yeah, so that can be one of the approaches. But if you have any certain modeling approach, or if you want to discuss on solution for your particular application, please do get in touch so we can discuss further on this.
So thank you so much, Bharat, for answering those questions and for the great presentation. It was a pleasure to have you with us. So here we come to the end of the webinar. Thank you all for attending, and we hope you all enjoyed this interactive presentation while carrying back a gamut of information from the model multiphysics world. The Volt Post appreciates feedback, so don't forget to share your feedback to us. Thank you so much.
Yeah, thanks, Manpreet. Have a nice day, everyone, and thanks for your time.